Okay, hello everyone. This is Siddhartha Pramanik. So I am a research scholar from the Department of Mathematics, IIT Kharagpur. So this is the week 6 for the course Introduction to Abstract Group Theory. So I am supposed to solve some sample problems related to the content of week 6. So I will start by writing the keywords of week 6. Then I will write down the problems which I am going to solve. So meanwhile, if you have any doubt, you can unmute yourself and ask, or you can write it in the chat box. So in previous week, uh, we started with transpositions, which are basically two cycles. Then we have characterized permutations in even and odd permutations. Next, we have saw what is meant by sign of a permutation. Then we have saw the group of all even permutation known as alternating group. Denoted by an, and then we move on to another topic which is known as group accents, and also we have saw orbit of group accents. So these are the main topics of previous of this week. So let me start some problems on even and odd permutations, then I will move on to group accents. So the first problem is basically on so which when an n cycle is even or odd. So let's try to see that first. So it will be very useful. So let n be a positive integer and sigma be a n cycle. So the question is, if n is even, then is sigma a odd permutation or even permutation? So sigma a even permutation or odd permutation? So okay. So given is sigma is an n cycle, means it is of the form a1, a2 dot dot up to an, and n is a positive integer. So you need to see when sigma is odd permutation and when sigma is even permutation. So let sigma is the n cycle a1, a2 up to an. Now let's take case 1. It is given that sigma n is even. So if first of all, we can break this sigma as a1 a2 times a2 a3 and so on up to an minus 1 an. So this is product of transpositions, right? And how many transpositions are here? So it is basically n.
N minus 1.
Sorry, what?
N minus 1 transpose.
Yeah. So sigma is product of n minus 1 2 cycles. So if n is even, n minus 1 is odd, so sigma is odd permutation. So n is even means n is 2n, sorry, n is equals to 2k. So n minus 1 is 2k minus 1, which is odd. So sigma is odd permutation. So then this is the answer of this question. But if we assume n is odd, then also the reverse thing happen, right? So let me put as remark. So n is odd implies n cycle is even permutation, and n is even means n cycle is odd permutation. So this thing we should remember, because we will be using this thing so many times. So let's see a simple problem which can be done using this one. Okay, so that the cycle 1 2 3 4, so it's a 4 cycle, uh, cannot be written as product of 3 cycles. Okay, so if okay, let's put this as sigma. So it means sigma cannot be written as sigma 1 up to sigma r, where sigma i's are 3 cycles. So we need to prove this. So can you see why this is happening?
So 3 cycles are even and 4 cycles are
Yeah,
odd.
so
So
here sigma is a 4 cycle, so it's a odd permutation, and 3 cycles are always even permutation, and also product of even permutations are even. So sigma cannot be a product of even permutations. So let me write down that. So here sigma is a 4 cycle, so it is a odd permutation, and 3 cycles are even permutation. So sigma cannot be written as product of even permutations. So basically sigma does not belongs to the subgroup of even permutations, and product of 3 cycles belongs to an. So that is also a reason. So let's move ahead. So we have saw if sigma is even permutation, then sigma inverse is also even, right? So what happens in case of odd permutation? So let sigma be an odd permutation. So is sigma inverse a odd permutation? Yeah. Do you have any guess for this? So given sigma is a odd permutation, so what can we say about sigma inverse? Is it odd or is it even?
It is also odd permutation.
Yeah. So basically it is if and only if. So inverse. So let sigma equals to let's say sigma 1, sigma 2 up to sigma n, a product of n two cycles. So then n should be even, right? Because n should be odd because sigma is an odd permutation. So what is sigma inverse? So it is basically inverse of this product, and inverse of this product is sigma n inverse times sigma n minus 1 inverse dot dot up to so on sigma 1 inverse, because it the reverse, sorry, the order will get reverse when we take inverse. But this sigma I, these are two cycles, means order of sigma I is 2. So sigma I inverse, it is itself. So it is same as sigma n minus 1 dot dot up to sigma 1. So it is also a product of two cycles. So sigma inverse is a product of n two cycles. So hence sigma inverse is a odd permutation. I hope this is okay. So what I am saying is this is if and only if. So sigma is odd if and only if sigma inverse is odd. So, so let me put that as remark. So sigma is odd if and only if sigma inverse is odd. So we have proved this side. So for converse, note that sigma equals to inverse of sigma inverse. So sigma inverse is odd, implies its inverse is also odd. So sigma is odd. And same happens for the even permutations. So this is also worth remembering. Okay, this is problem number 3. So let's problem number 4. So we have seen when an n cycle is odd or even, we have seen inverse of an odd permutation is odd. Now what about product of permutations, when it is even or when it is odd? So let alpha and beta are two permutations in Sn. So then this product is even, okay, let's say it is an even permutation, if and only if both alpha beta are even or both alpha beta are odd. So this product will be even only if either both are even permutation or both are odd permutation. Okay, so let's see a proof of this. So let us write alpha beta as product of transpositions. Let alpha is equals to sigma 1, sigma 2 up to sigma n, a product of n 2 cycles, and beta equals to tau 1, tau 2 up to tau m. This is also a product of uh, m2 cycles. Now then, alpha beta we can simply write this product times this product. So let's write that. So it is sigma 1 up to sigma n, tau 1 up to tau n. So it is a product of n plus m 2 cycles. So we need to check when this alpha beta is even permutation, right? So alpha beta is an even permutation if and only if n plus m is even. Now this is sum of two integers. So when it is even. So if and only if both n and m are even or both n and m are odd. So either both n comma m are even or both n comma m are odd, right? So that will imply either both alpha comma beta are even permutations or both alpha comma beta are odd permutations. So this completes the proof. So is it okay? So this product is even if and only if both alpha beta are even or both alpha beta are odd. So now the question is, when this product is odd,
When one is odd, one is even.
yeah, so both cannot be same sign. So alpha beta is an odd permutation if and only if one of alpha beta okay, Okay, let me write in a different way. If and only if alpha and beta has different signs. So we know sign of a permutation, right? So sign of a permutation sigma, it is defined as 1 when sigma is even, and it is -1 when sigma is odd. So we are using that concept. So both signs are different means both cannot be even, both cannot be odd. So okay. So we have seen inverse of odd permutation is odd. Also we have seen about the product. So one thing is left. It is about conjugation. So question is if sigma belongs to Asian and if tau sigma tau inverse. So this is a conjugate element of sigma, right? So how the signs of these permutations are related. So let me write the question precisely. So let sigma comma tau belongs to Sn. So then sigma is an even permutation if and only if tau sigma tau inverse is an even permutation. So if sigma is even, if and only if it's conjugate, it is also even. Okay, so let's prove this. This is also not that difficult. So let's write sigma and tau as product of two cycles. So let sigma is equals to sigma 1, sigma 2 up to sigma n. It is product of n two cycles, and tau equals to tau 1 up to product of tau n. So it is product of m2 cycles. So what is sigma inverse then? So sigma inverse is inverse of this product, and this is basically tau m inverse up to tau 1 inverse. But these are two cycles. So inverse of n2 cycle is itself. So it is tau m to tau 1. So tau inverse is also a product of m2 cycles. So we have seen it earlier also. So now what is tau sigma tau inverse? So it is basically product of tau 1 up to tau m, sigma 1 up to sigma n, and again tau m up to tau 1. So in this product we have 2m plus n 2 cycles. So tau sigma tau inverse is a product of 2m plus n 2 cycles. So thus tau sigma tau inverse is an even permutation if and only if this number 2m plus n, it is an even number. So 2m plus n is even. Now when this number is even, so 2m is always even. So it depends on this n only. So if and only if n is even. And that is true if and only if sigma is even. So this proof is also complete. So I hope this proof is okay. So and permutation is even if and only if its conjugates are also even. So same can be said for odd permutation also. So let me mention that also. So sigma is odd if and only if tau sigma tau inverse is odd. And the proof follows the exactly the same way as we have done for the even case. Okay, now let's do some concrete problems. These are some theoretical problems. So in earlier life season, we have seen how many elements of some fixed order are there in SN. So we have done some problems of this type. Now we want to do some problems. Instead of SN, we will going to take AN. So question is uh, how many elements of order 4 are there in S6? Sorry, not S6, it is A6. So Sn is a finite group. Its order is n factorial, we know. And An is also a finite group. So every element of n is of finite order. There are only finitely many of them. So this question makes sense. So what is the starting point of this problem? First of all, we need to check there exists some element of order 4 in A6 or not. Right? So uh, first we need to check if there exist elements of order 4 in A6 or not. So how to check this one? So for this, we first need to see how the elements of order 4 in S6 looks like. So now an element of order 4 in S6 has the following disjoint cycle structures. So remember that in Sn, if sigma belongs to Sn, then sigma can be written uniquely as product of disjoint cycles. So that is known as disjoint cycle structure of sigma. So in that structure, every element can be written, every element of Sn can be written. So we are in S6. So in S6, what are the different cycle structures? So first is one cycle, or means the it is just the identity element because we don't write one cycle, or it can be two cycle, or it can be three cycle, up to so on it can be six cycle. But there are other elements, right? Like it can be a product of two cycle, product of a two cycle and a three cycle. Okay, let me write in a more compact form. So it is one cycle, it is two cycle, similarly three cycle, six cycle. Product of two cycles, product of a two cycle and a three cycle, product of three cycles, and what else are there? Product of a two cycle and a product of four cycle. Anything else is there? So these are the all possible cycle structures in S6, right? So among these cycle structures, uh, so which elements has order 4? So first of all, it can be a 4 cycle. That means it is of the form A, B, C, D. So it is a 4 cycle, or in our notation it is of this form, or it can be a product of 4 cycle and a product of 2 cycle. So it is of this form. So only these two types of cycle structures has order 4 in S6. But among these elements, which elements are in A6 means which are even permutation. So because we only need to count in A6, right? So now observe that a 4 cycle is an odd permutation. So this cannot belongs to A6. But this is an even permutation. And this has order 4. So we only need to count the number of elements of this form. Now, uh, 4 cycles are not in A6, but cycle permutations of the form A, B, C, D, a product of 4 cycle with a product of 2 cycle. These are in A6. And these are the only elements of order 4 in A6. So we need to count total number of elements of this form in A6. Now how to count that? So we are in A6, right? This is subset of A6, and here these are all permutations from 1 to up to 6 to itself. So we have at most 6 indexes. So this A can for A we have 6 choices. Okay, let me write it here: A, B, C, D, E, F. So this A has 6 choices. This B has 5 choices. So C has 4 and D has 3 choice. And E has ultimately 2 choice, F has 1 choice. But remember that a 4 cycle, it can be written in 4 ways. So this 4 cycle, it is same as if we start with at B. Similarly, we can start it at C also. And similarly, we can start it at B. So these are all, these 4 permutations all are equal. So a 4 cycle can be written in 4 ways. So uh, those gives the repetitions. So let me write it here. So the number of elements of order 4 in A6 equals to, so 6 choice, 5 choice, 4, 3, and 2 choice, 1 choice. So as I have told, a 4 cycle can be written in 4 ways. So those gives the same permutation. So we need to divide this one by 4. Similarly, a 2 cycle can be written in 2 ways. So we need to divide it by 2. So this is the total number. So this is exactly equals to 90. So is it okay? Do you have a doubt in this? Okay. So I hope you have understood this one. So now let's move on to another problem.
I have a doubt.
Yeah, tell me.
While dividing for repetition, don't we need to divide by 4 factorial and 2 factorial?
Not 4 factorial. We have exactly 4 repetitions, right? Not 4 factorial repetitions.
Okay.
Yeah. Uh, Anything else?
No.
Okay. So we have seen order of Sn is exactly n factorial, and order of An is n factorial by 2, right? We have see this in lectures. So that means exactly half of elements of Sn are even permutations. So something more general is true. Let me write down that as a problem. So let H be a subgroup of Sn. Then so that either every element of H is an even permutation, or exactly half of the elements of H are even permutation. So that means H is a subgroup of Sn. So either H is subset of N, or exactly half of the elements of H are, so either H subset of N, or H has exactly half elements, means order of H by 2 elements which are even. Okay, so I hope you have understood the question. Okay, so let's prove this. So observe that if every element of H is even, then we have nothing to prove. So if every element of H is an even permutation, then we have nothing to prove. Right? So assume H contains a odd permutation. So assume H contains an odd permutation. Let's say sigma. So now we have to prove H contains exactly uh, half of the elements of H are even and half of the elements of H are odd. So how to do that? So let A be the number of even permutations of H, and okay, not N, let's say N be the number of even permutations of H, and M be the number of odd permutations of H. So then cardinality of H is basically N plus M. So we need to prove, we need to prove N is exactly equals to M, right? So then we are done. So how to prove N is equals to M? So we will show N is less equals to M and M is less equals to N, the classical way. So what we have? we have an odd permutation in H. So n is the total number of even permutations, right? So suppose uh, tau 1, tau 2, tau n are all even permutations in H, right? Then, so if we multiply sigma with a odd with a even permutation, then what it will be? Means this product sigma tau 1, sigma tau 2, sigma tau n. So sigma tau 1 is even or odd? It is odd, right? Because sigma is odd and tau 1 is even. So product should be odd permutation. So then these elements sigma tau 1, sigma tau 2, sigma tau n are odd permutations in H. Okay. And also they are distinct. Sigma tau I is not equals to sigma tau j or I not equals to j. Can you see why? Because tau 1, tau 2, tau n are distinct permutations. Means, so if sigma tau I is equals to sigma tau j, so use the cancellation law. So we can multiply with sigma inverse both side. So that will give tau I is equals to tau j. But tau i's are distinct. So this implies sigma tau 1, sigma tau 2, sigma tau n are also distinct. But these are even permutations. Sorry, these are odd permutations. So in H, there are at least n odd permutations, right? So this implies H contains at least n odd permutations. Now, M is the total number of odd permutations of H. So n should be less equals to m, because m is the total number of odd permutation and H contains at least n permutation. So we have proved one side. Now let's do the other side. Now we can also assume let's say sigma 1, sigma 2 up to sigma m are all odd permutations of H. So these are the total all odd permutations in H. So if we multiply this with sigma, means sigma times sigma 1, sigma times sigma 2, sigma times sigma 1. So these are even permutations, right? Because both sigma and sigma 1 is even, so their product is even. So are even permutations in H, and also they are distinct by the similar logic. Sigma I not equals to sigma times sigma j. for I not equals to j. So similar logic as we have done in this case. So this means H contains at least m even permutations, right? But n is the total number of even permutation of H. So m should be less equals to n, because n is the total number of even permutations in H. So now combine these two, n is less equals to m and m is less equals to n. So hence m is equals to m. So the number of even permutation and the number of odd permutation are equal in H. Thus, exactly half of the elements of H are even permutations and exactly half is odd. So, did you understand this? So, is it okay? So, one thing can be observed from this, and let me put that as remark. So, uh, if H subset of Sn is a subgroup, then either H is subset of An, means all elements of H are even permutation, or exactly half elements of H are even, right? So order of H is even. So either H is subset of N or order of H is even. So are you able to see this? Okay. Now let's see some application of this problem. So this is problem number 7. So suppose H is a subgroup of Sn of odd order, then show that H is subset of An. So if H is a subgroup of Sn, of odd order, then H has to be subset of A. So let's use the previous problem. Now, uh, either, so I don't need to write anything, just, so see this one. So if H is subgroup of Sn, then either H is subset of An or order of H is even. So this is just a contrapositive statement, right? So, is it okay? Can you see this? Or shall I explain more? Okay, so I hope this is okay. Let's see one more problem of this type. So let H be a, sorry, let sigma belongs to S10 has order, let's say, order 5. Then uh, what is sign of sigma? So can you do this? So sigma is an permutation in S10 which has order 5. Then what is sign of sigma? Means sigma is odd or sigma is even. Can you conclude this? Just try for a few moments. Yeah, do you have any guess? You can use the previous result.
It has order 1.
Sorry, can you repeat?
It has order 1.
Order or sign?
Sign 1.
Yeah, so means sigma has to be an even permutation. So let me write the solution. So let's take H be the subgroup generated by sigma, right? So then order of H is same as order of sigma, and that is 5, and it is odd order. So by previous problem, H has to be subset of A. So that implies sigma belongs to A. So sigma is an even permutation. So that implies sign of sigma is 1. Okay, I hope it's okay. So let's see one more typical application of this problem. So how many elements are there. Okay, how many elements of order 9 are there in, let's say, S11? Okay, 9 is too big. It's something more. Order maybe 3 in S7 or S6. S6. Okay, can you, sorry, not S6, A6. So how many elements of order 3 are there in A6? Can you do this? So in previous class we have done number of elements of order 3 in S6. So in previous season we have done all problems of this type in SN. Now we are doing in AN. So just try this. If you have any answer, you can tell me.
Two elements.
Only two. How? Can you explain?
So, like how we have done in the fifth one, first they have written the what are the possible ways of writing the permutations.
So possible two cycle structures are there, but not only two elements, right? Okay, first of all, observe that 3 is odd. So if we use the earlier problem, so it is more general. Actually, let me put that remark. Then I will come back to this problem. So in this problem, instead of S10, if we take Sn, and instead of 5, if we take any odd, then also this result is true by the similar way. So remark, if sigma belongs to Sn has odd order, then sigma must belongs to An. So what does that mean? So all elements of Sn of odd order are actually in An. So here elements of order 3 in A6 are same as elements of order 3 in S6, right? So we only need to count elements of order 3 in S6. So let sigma belongs to S6. Sorry, okay, let me write clearly. Now all elements of order 3 in A6 are same as all elements of order 3 in S6. So we need to count in S6. So we need to count number of elements of order 3 in S6. So let's start by the first step, which is we need to count the possible cycle structures of elements of order 3 in S6. So now the possible disjoint cycle structures of elements of order 3 in S6 are, first of all, it can be a 3 cycle because 3 cycles has order 3, or it can be product of 2 3 cycles. To disjoint 3 cycles, right? So I hope you remember, if sigma belongs to Sn and sigma is written as this is the disjoint cycle structure, then how to found the order of sigma? This is same as LCM of order of sigma 1 up to order of sigma n. So we are basically using this result to found the possible cycle structures. So this element has order 3 and this element has also order 3. So we need to found how many elements are there of this form and also how many elements are there of this form. So let's do this. So again, A has 6 choice because we are in S6. So B has 5 choice, C has 4 choice. But this is a 3 cycle which can be written in 3 ways. So we need to divide it by 3. So this is same as 6 times 5 times 4 by 3. So this is same as 40. Is it okay? Okay. So now number of elements of this type. So again, A has 6 choice, B has 5 choice, C has 4 choice, and this is a 3 cycle, so we need to divide it by 3. And D has 3 choice, E has 2 choice, F has 1 choice. So again we will divide by 3 because it is a 3 cycle. But these are disjoint 3 cycles, so they commute, right? So it can be written as DEF times ABC also, but both these cycles are permutations are same. That means we need to divide again it by 2. So did you get the point? So in this case the total number is 6 times 5 times 4 by 3, 3 times 2 times 1 by 3, and whole by 2. So this is also 40. So the total number of elements of order 3 in A6 is equals to 40 plus 40, which is 80. So is it okay? Do you have any doubt in this? Okay, so let's move on to another problem. So number 11. So this is a different type of problem, but it is important. So let n is greater than 1, an integer, then so that uh, every element of Sn can be written as a product of the elements of the form of this two cycle, where k lies between 2 to n, means 1 2 1 3 and so on up to 1n. So every element of Sn can be written as product of elements of this type, of these two cycles. So here are n minus 1 two cycles, and the problem is every element can be written as some product of these two cycles. So that means these elements are generators of Sn, means Sn can be generated by this set. Okay, I hope you have understood this problem. So let's see a proof for this. So first of all, recall that every element of Sn can be written as product of two cycles or transpositions. Right? This we have seen in the lectures. So let's take an arbitrary element sigma from Sn. So then sigma is product of two cycles. Let's say sigma 1 up to sigma r, product of two cycles. So if we can prove that each of these two cycles, sigma 1 up to sigma r, can be written as product of this type of elements, then we are done, right? So if we can prove every two cycle of SN can be written as product of elements of the form of this two cycle, then we are done. Right? I hope this is clear for you. So then sigma 1 is product of this type of elements. Same for sigma 2, same for sigma r. Then we will substitute those things here. So then sigma will be product of this type of elements. So we have reduced our problem from arbitrary element of Sn to two cycles. So we need to prove it for only two cycles. So let I comma j be a two cycle in Sn, and also assume okay, we don't need to assume anything. So it is an arbitrary two cycle. So we need to prove this can be written as product of this type of elements. So observe that this cycle, it can be written as, now I comma j clearly belongs to 1 2 up to n, right? Because it is an element of Sn. So this can be written as 1 comma I times 1 comma j times 1 comma I. So you can verify that this product will give you I comma j, this cycle ij. So this is the required result which we want to prove. So this completes the proof. So is it okay? Okay, so we have done even odd permutations, sign of permutation, also the alternating group. Now let's move on to the another topic, which is group actions. So this topic is somewhat geometrical. Let's try to see why. So meanwhile, do you have any doubt in between? Okay, so let's see some more examples of group actions, which will be used in the later lectures also, and these are interesting because of their geometrical structure. So some more examples of group actions. So the first example is, let's take G be the group as R star comma dot, means the non-zero real numbers under multiplication, and S be the set Rn, means the set of all n tuples of real numbers. Now for G belongs to G and A1 up to AN belongs to Rn, let us define this function as, let's not take G, let's take R because it's real number. RA1, RA2, RAN. So this is a group action when G acts on S. So I hope you are able to understand the function. So let's try to prove this. So what is group action? So we have a function from G cross S to S, which we denote it by just GS, right? And it has to satisfy two properties. First of all, E dot S is equals to S for all S belongs to S, and the second is associativity. G1 dot G2 dot S is same as G1 G2 dot S, and this is true for all G1 G2 in G and for all S in S. So we need to verify these two axioms, then it will be a group action, means this function will be group action. So in R star, identity is the 1. So 1 times this element, okay, let's write, okay, for A1 up to AN belongs to Rn, this product is same as 1 times A1 and so on 1 times AN. So this is same as A1 up to AN. So the first axiom is satisfying here. So it is trivial, right? So let's see the second one. Second one is also trivial, but let's see this. So let R1, R2 belongs to R star and A1 up to AN belongs to Rn. So then R1 dot R2 dot A1 up to AN is same as R1 dot R2A1 R2A2 dot dot up to R2AN, and this is same as R1 R2A1 R1 R2A2 R1 R2AN, and we can write this as R1 R2 dot A1 A2 up to AN. So that is exactly what we need, right? This is the second axiom. So both of these axioms are satisfying. So this is a group action. So I have done this rigorously because in other examples, which are in the assignment, you may need to check which are group actions or which are not. So you just need to check step by step. That's all. So it is a group action. Now, what are the orbits of the elements? So the question is how the orbits looks like. So to visualize this, let's do it for just n equals to 2 so that we can draw the graphs. So take n equals to 2. Now for a point a1 comma a2, let's say it is a, belongs to R2. What is the orbit of a? So orbit of a is just denoted by O subscript of a. It is the set R dot A such that R belongs to G, which is our R star, right? This is by definition. But what is this set? This is actually RA1, comma RA2 such that R belongs to R star. So if we just draw the graph, so this is x-axis, this is y-axis, means it is the R2 plane. Let's say our A1, A2 is something lies here, this point. Then its orbit is nothing but this straight line. But R belongs to R star, right? So we don't have 0. So we have to, so it is not just this straight line, we have just punctured at 0. So it is union of this straight line. This straight line, union this straight line. So orbits are basically straight lines, but which has break at the origin. So what is orbit of 0 then? So orbit of the point 0 comma 0 is just r times 0 comma r times 0 such that r belongs to r star. So it is just singleton set 0. So if we take the point 1 comma 0 here, then what is the orbit? Orbit of 1 comma 0 is just r dot 1 comma 0 such that r belongs to r star. So this is r comma 0 such that r belongs to r star. Sorry, I have taken wrong one. So 1 comma 0 is here on the x-axis. So orbit is the whole x-axis except the origin. So it is the whole x-axis except the origin, right? So orbits of non-zero points are straight line which does not contains the origin. And orbit of the 0 is only singleton set 0. Okay. Now let's see some other examples. So this is the first example. Now let's see one concrete abstract example.
Sir, I have one doubt, sir.
Yes, tell.
Sir, how to write this is on the straight line? The orbital is straight line because RA1, RA2 is any point in XY plane. How to write in
No, no,
particular
no.
on the
This
straight line? How to?
this is scalar multiple of A1, A2, right? RA1 and RA2.
Okay, sir. Any point in XY plane is in the space. not on straight line. How to write this in particularly on
No,
straight
no.
line?
As you take a fixed point, just like 1, comma 0 on the x-axis. So we have saw what is the orbit of this point. It is just r dot 1, comma 0. This is r, comma 0, and r can be any real number. So it
Okay, sir.
is
Sir,
it is
but
the
in general, sir, in general,
yeah.
first orbit of A, how to write this? It is a straight line.
Uh, it is actually we are varying all points on this line actually, because we are varying this r. R is
Sir,
varying from,
only on this line, or R is any real number?
yeah, r is only real number, but
Sir.
this set is multiple of this a1 a2, right? So it is on the straight line only.
Sir, how to write this is on that line. A1, A2 is on a line, straight line, sir, or in space, sir?
A1, comma a2 is a point, and
It,
r
it,
a1, comma r a2, this lies on this straight line passing through a1 a2. So r a1
sir,
r,
A1, A2 is arbitrary points, arbitrary
yes,
number.
arbitrary point lies in this straight line passing through a1 a2,
Why we have to take on a straight line, sir?
because r is just single dimension variable, right?
Okay.
Can you see this thing? Because r, we are just scalar multiplying r a1 and r a2. So one thing you can do is you just write the equation of the straight line passing through the point a1 a2, then you try to see how those points looks like. Okay, then I think you can realize. So the straight line passing through a1 a2 and the origin, you just write the equation of that. Then you will see that every point of that line is of this form. Yeah, you try it on your own. Then if you still have doubt, you can ask me in the next season.
Sir.
Okay, so let G be an arbitrary group, and H be a subgroup of G. Then set, okay, let's take S is equals to G mod H. So remember that H is only a subgroup, not a normal subgroup. So this G mod H is the set of all left cosets of H in G. So it is not a it is not a group. It will be a group only when H is normal subgroup. But we only need set structure. So it is a set. So we will define an action of G on S. So for G belongs to G and a left coset AH belongs to G mod H, define this map which goes to G dot AH as just GA of H. Okay, so then also it is a group action. So then G acts on S. So the proof is trivial. So I want you to check this. Proof is not difficult. So I want to see how the orbits looks like. So proof, let's say it is exercise for you. So what are the orbits? So if you take an arbitrary element, let AH belongs to S, which is G mod H, then what the orbit of this element? Can you guess what is the orbit of this element? Try to see by the definition. So what is the definition? It is G dot AH, where G varies over all group, right? Varies over all elements of the group. So what this set? Okay, let's take normal subgroup. Otherwise, the multiplication will not make sense. Oh, sorry, we don't need normal subgroup. Sorry. Yeah, so can you see? So this is just by definition, it is GAH such that G belongs to G. So my claim is this is the whole set G mod H. So it is clearly subset of G mod H, right? But it contains all left cosets. So why it contains all left cosets? So if let's say BH belongs to G mod H, then if we take G equals to BA inverse, so this will imply G times AH, it is in the orbit. But what this element? This is B A inverse dot AH. This is same as B A inverse A of H, and this is same as BH. So this implies BH is in orbit of AH. So G mod H is subset of orbit of AH. So orbit is the whole set. No matter what is your left coset, orbit is the whole set. So that means this has only one orbit. So there exists only one orbit. So for this group action, there exists only one orbit. And this type of group actions has a name. So let me also mention that. If G acts on S and there is only one orbit, then this group action is called transitive. So this group action is a transitive group action. This is the second case. Is it okay? Okay, now let's see one concrete example, and this one is interesting. So let's take G as Sn and the set S as Rn. Okay, then for sigma belongs to Sn and element A1 up to An belongs to Rn, define sigma dot A as the n tuple A sigma 1, A sigma 2, A sigma n. So what we are doing? So we are taking this n tuple and we are just permuting its coordinates. So applying sigma on A, that means we are just permuting the coordinates of A by using sigma. So this is a group action. So let me prove this. This is a group action. So what is identity permutation dot A? So this is same as E of identity permutation of 1, E of 2 dot dot E of A of E of n. But the identity permutation maps 1 to 1, 2 to 2, and so on up to n to n. So this is same as A of 1, A of 2 up to A of n. So this is our A. This is true for all A in Rn. So our first axiom satisfied. Now let sigma 1, sigma 2 belongs to Sn and A equals to A1 dot dot up to An belongs to Rn. So we need to prove sigma 1 dot sigma 2 dot A is same as sigma 1 sigma 2 dot A, right? So let's do this. So then sigma 1 dot sigma 2 dot A, what is this? This is sigma 1 dot A of sigma of 1 comma A of sigma of 2 to A of sigma of n. Now apply sigma 1. So this is this is sigma 2. So this is sigma 1 of sigma 2 of 1 and so on, A of sigma 1 of sigma 2 1. This is same as A of sigma 1 sigma 2 evaluated at 1, and this is same as sigma 1 sigma 2 evaluated at n. So this is sigma 1 sigma 2 dot A. So this is a group action. So it is trivial also. There is nothing difficult here. So the interesting part is what are the orbits. Now let's check the orbits for some elements. So I hope you have understood the group action. Do you have any doubt in this mapping? Okay, so if you have no doubts, then let's try to see how the orbits looks like. So first, let's uh, let's try to see the orbits of elements of this form. So here n minus 1 tuples. So in first coordinate we have 1 and other coordinates all are same for some x belongs to R. Then what is the orbit of can you guess what is orbit of this element? Or how many elements are there in the orbit? Any guess? So let's try to see by the definition. So orbit of A is by definition sigma dot A such that sigma belongs to Sn. So basically it is the set of all tuples sigma applied on this tuple such that sigma belongs to Sn. So how what are the elements are there in this orbit? So sigma just permutes the coordinates, right? It just interchanges the coordinates. So if let n is 3, so we have S3 and the set is R3 and A is your element 1 comma x comma x. Now let's apply this permutation 1 2 on A. Then what does it do? It is just x comma 1 comma x. It just permutes the first and second coordinate. So first coordinate 1 goes to 2 means first coordinate goes to second coordinate and second coordinate goes to first coordinate. So what is 1 3 of A? So first coordinate 1 goes to 3 means first coordinate should go to third coordinate. So it is just x x1. So basically now can you guess what is the orbit? Okay. So basically if sigma varies over all permutations, right? So if sigma of 1 is equals to 1, means sigma fixes 1, then sigma dot a is same as a, because in the other coordinates from second coordinate, third coordinate, all elements are same, but this first coordinate is fixed. Other coordinates we don't, uh, if, if it is changing, it does not matter. So the question is, what happens if sigma of 1 not equals to 1? So then sigma of 1 belongs to the set 2, 3 up to n. So the first coordinate can map to any of the coordinates 1, 2 up to n. So in all those cases, we have 1 in that coordinate. So basically, orbit of A is 1 comma x comma x, x comma 1 comma x up to x, and so on, x comma x up to 1 x. So orbit consists of this type of elements. So in which one lies in the first coordinate, here one lies in the second coordinate, so one lies in the n minus 1th coordinate, and here one lies in the nth coordinate. So did you understood this? Okay. So this orbit has exactly n elements. So we have found orbit of just this type of elements. Okay. Now let's try to see orbit for one more type of element. So let uh, A is equals to x1, x2 up to dot dot xn belongs to Rn, where xi's are all distinct. So in the earlier case, we have only first coordinate 1 and other coordinates are all same, fixed element x. But here we are taking all different coordinates. So what is the orbit of A then? So what is this set? So this time can you guess anything? Or exactly how many elements are there in the orbit? So earlier we have just n elements in the orbit. Okay, so let's write the definition again. So it is just sigma dot A such that sigma belongs to Sn. Means sigma varies over all elements of Sn. So this is x of sigma 1, x of sigma 2, x of sigma n, such that sigma belongs to Sn. So let's try to see how many elements are there in this orbit. So sigma belongs to Sn, right? So sigma 1 can go to 1, 2 or up to n. So it has n choices. So sigma 1 has n choices. So that means sigma 2 has n minus 1 choices. So sigma 1 has n choice, sigma 2 has n minus 1, sigma n minus 1 has 2 choice, and sigma n has only 1 choice. So total there are n into n minus 1 dot dot up to 1 is n factorial choices. So that means this orbit has n factorial elements. And these are just permutation of this exercise. Nothing else. Only the permutation of exercise. So it is x1, x2, xn. This one element is there. x2, x1 dot dot up to xn. This is another element. Just we are permuting the coordinates. So how many times we can permute? Because we are permuting using all elements of Sn, and there are n factorial elements. So we have n factorial elements in this orbit. So is it okay? Okay, so this one is complicated example. Now let's see the final example, which is bit simpler. So it is problem D. So let uh, G be the multiplicative group of two roots of unity, 1 and minus 1, and S be another group, let's say G prime. So our set is also a group in this case, which is G prime. So now define. So for G belongs to S, let us define 1 dot G as, means 1 dot G as G, and minus 1 dot G as G inverse. Okay, so I hope this function is clear. So then G acts on S. So proof is very easy, you can check. So my interest is only on the orbits. So what are the orbits? So let G belongs to S belongs to G prime. Then what is orbit of G? Can you say this one? So by definition, it is just 1 dot G and minus 1 dot G, because our group has only two elements. Now what is this set? This is same as G and G inverse, right? So our orbit is exactly consist of G and its inverse. But in some cases, G equals to G inverse. So orbit can be singleton set also. It may not be a double T. So this group action is useful. So maybe in the next season I will do some application of this group action. So now you will not be able to realize the importance of this group action, but maybe later. Now let's do one more. Let's say E. So in the class, in the lectures, we have saw G acts on itself by conjugation, right? Means if we take G comma A, then we have mapped it to G inverse. So this can be done in more general. So let's write that. So let G be a group and N be a normal subgroup of G. Now let's take S is equals to N. So define from G cross S to S by mapping G comma A to G dot A as G inverse. Now remember, N is a normal subgroup. So this element lies in N, which is S. So this function is well defined. Now the fact is, then G acts on N. Means this is a group action. So in the lectures we have taken G itself, but that can be replaced by any normal subgroup. So that is the case here. So proof is easy. I don't want to do the proof. My interest is in the orbits. So for A belongs to N, what is the orbit of A? So it is just G dot A such that G belongs to G. This is by definition G inverse such that G belongs to G. So this element is known as conjugate of A by G. So this set is the collection of all conjugates of A. This has a name. This is known as conjugacy class of A. So in the next week lectures, I hope you will see this term. In the next week lectures, you will be see class equations and conjugacy classes. So this is the orbit. So for identity element, what is the orbit? So for identity element, it is G inverse such that G belongs to G. So it is singleton set. Even if A belongs to N as well as A belongs to the center, then also this orbit is singleton. When its conjugacy class is a singleton set. So these things you will see later in this next week. So I hope I have done few examples which are interesting, and I have covered most of the topics of the previous week. Group actions, orbits. Okay. So I'm already over time. So we can wind up this season now. So So if you have any doubt, you can ask. So if you have no doubt, then we can wrap up. Okay, bye then.